The Schrödinger equation of multi-electron molecules are even more difficult to solve. Like in the atoms, the overall electronic wave function in a molecule can be approximated by the wave functions of individual electrons. The wave functions of individual electrons are called molecular orbitals. The electrons occupy molecular orbitals in molecules, like they occupy atomic orbitals in atoms. The principles of electron configuration in molecules are like those in the atoms. They are Aufbau principle, Pauli exclusion principle, and Hund's rules. The electron configurations of molecules can be illustrated with the molecular orbital diagrams. In the molecular orbital diagrams of diatomic molecules, the atomic orbitals are represented with horizontal lines on the two sides. The molecular orbitals are represented with horizontal lines in the middle. The altitudes of the lines represent their relative energies. Here, we use hydrogen molecule as an example. The atomic orbitals are the 1s orbitals of the hydrogen atoms. They have the same energy. The bonding orbital has a lower energy, while the antibonding orbital has a higher energy. The dashed lines connect the molecular orbitals and the atomic orbitals which constitute them. Electrons are represented by arrows showing their spins. All the electrons in the atomic orbitals and the molecular orbitals are shown. For example, in the hydrogen atom, the 1s orbital is occupied by one electron. In the hydrogen molecule, the two electrons occupy the same bonding orbital because it has the lowest energy. And they have opposite spins. Then, let's have a look at the molecular orbital diagram of the dihelium molecule. Each helium atom has 2 electrons in its 1s orbital. There are totally 4 electrons in the molecular orbitals. They occupy both the bonding orbital and the antibonding orbital. The total energy of the bonding and antibonding orbitals is higher than twice of the atomic orbitals. As a result, the dihelium molecule is not stable. It must dissociate into 2 individual atoms. The molecular orbital diagram of dioxygen molecule is shown below. Due to larger overlap of 2 pz orbitals, the energy difference between bonding sigma 2 pz orbital and antibonding sigma 2 pz orbital is greater than the energy difference between bonding pi 2 px orbital and antibonding pi 2 px orbital, which is equal to the energy difference between bonding pi 2 py orbital and antibonding pi 2 py orbital. The molecular orbital diagram of diboron molecule is also shown below. You can easily find the difference in the molecular orbital diagrams. In the molecular orbital diagram of diboron molecule, the energy of the bonding sigma 2 pz orbital is higher than the energy of bonding pi 2 px and bonding pi 2 py orbitals. The strange behavior of the molecular diagram of diboron molecule is caused by the sp mixing. We will not discuss the details of the sp mixing in general chemistry. The sp mixing exists in diboron, dicarbon and dinitrogen molecules. It does not exist in dioxygen, difluorine, and dineon molecules. Consider, if diboron molecule does not have sp mixing, what electron configuration should it have? Bond order is defined to be the number of electrons in the bonding orbital minus the number of electrons in the antibonding orbital, divided by 2. To calculate the bond order, we only need to consider the molecular orbitals made of the valence electrons. Here, we use dilithium molecule to difluorine molecules as examples. The bond orders can be easily calculated from their molecular orbital diagrams. The bond orders qualitatively describe the properties of the bonds. Generally speaking, a higher bond order leads to a smaller equilibrium distance and a higher dissociation energy. Thus, diatomic molecules with higher bond orders are more stable. The bonds with bond order 0 are too unstable to exist. A bond with bond order 1 is also called a single bond. A bond with bond order 2 is a double bond. A bond with bond order 3 is a triple bond. A triple bond is stronger than a double bond, while a double bond is stronger than a single bond. Here, I show you the shapes of the molecular orbitals of benzene. You can see how colorful and beautiful they are. Let's recall something you have learned in high school. The valence bond theory says that a covalent bond is formed between 2 atoms by the overlap of half-filled valence atomic orbitals. The electrons in the overlapping orbitals are shared by the atoms. The valence band theory can be represented with Lewis symbols and Lewis structures. The Lewis symbols is such a system in which the valence electrons are represented by dots around atom symbols. A straight line represents a pair of shared electrons. The Lewis structures are the representations of molecular structures using Lewis symbols. For example, the Lewis structures of oxygen and nitrogen molecules are shown below. You can see that the number of lines in a bond is equal to the bond order. The main difference between the valence bond theory and the molecular orbital theory is that the valence bond theory only considers the bonding between two atoms, but the molecular orbital theory has orbitals that cover the whole molecule. In molecular orbital theory, the electrons can be shared by many atoms. For example, the structure of benzene described by the valence bond theory is different from the molecular orbital theory. Matters have various magnetic properties. The magnetic properties of the matters composed of molecules are the results of the magnetic dipole moments of the molecules. The magnetic dipoles of molecules are mainly caused by the spin and motion of its electrons. If a matter has its magnetic dipole parallel to the external magnetic field, it is attracted to the region with stronger field. If a matter has its magnetic dipole antiparallel to the external magnetic field, it is repulsed by the region with stronger field. So, the magnetic properties of matter can be studied through their interactions with external magnetic field. The magnetic properties of molecules can be also explained by molecular orbital theory. Paramagnetism is the property that the induced magnetic dipole of matter by the external magnetic field is parallel to the external magnetic field. When there is no external magnetic field, the magnetic dipoles in the paramagnetic matter are randomly oriented, so the total magnetic dipole moment of the matter is zero. When an external magnetic field is applied, the magnetic dipoles are aligned in the direction of the external field like compasses. Therefore, the total magnetic dipole is parallel to the external field. When the external magnetic field is removed, the magnetic dipoles in the matter return to random orientation, and the total magnetic dipole moment becomes zero. The paramagnetism is caused by the unpaired spins. Unpaired spins have the tendency to be aligned in the direction of external magnetic field. For example, an oxygen molecule has two unpaired spins. More oxygen molecules have their magnetic dipoles aligned in the direction of the external magnetic field than those in the opposite direction. The paramagnetism of oxygen can be observed in such experiment. A super strong magnetic field is produced between two electromagnets. Then, liquid oxygen is poured into the gap between the two electromagnets. Instead of falling off, the liquid oxygen is stuck in the gap. The reason is that the magnetic field inside the gap is stronger than that outside the gap. So, the liquid oxygen is attracted towards the stronger magnetic field. It proves that oxygen is paramagnetic. The molecular orbital theory successfully predicts the paramagnetism of oxygen. Diamagnetism is the property that the induced magnetic dipole of matter by the external magnetic field is antiparallel to the external magnetic field. In diamagnetic materials, if there is no external field, the magnetic dipole moments of all the molecules are zero. With an external magnetic field, the motion of electrons produces magnetic dipoles in the opposite direction to the external magnetic field. When the external magnetic field is removed, the magnetic dipole moments return to zero. A molecule is diamagnetic if it has no unpaired spins. Water is a good example of diamagnetic matter. According to its molecular orbital diagram, water molecule has no unpaired spin. In an experiment, a little frog is levitated above a magnetic field over 16 Tesla. We know that a frog is mainly composed of water. The levitated frog proves that water is repulsed by a stronger magnetic field, so that water is diamagnetic. The molecular orbital theory successfully predicts it. A ferromagnetic matter is made of lot of small parts called domains. Each domain has its own magnetic dipole. If the magnetic dipoles of the domains are randomly oriented, they cancel each other, and the matter shows no magnetic dipole. When there is a strong enough external magnetic field, the magnetic dipoles of the domains are forced to be aligned in the direction of the external magnetic field. Even after the external magnetic field is removed, the magnetic dipoles of the domains are remained, so that the matter preserves its magnetic dipole moment. However, when the ferromagnetic matter is heated to a temperature called Curie temperature, it loses its ferromagnetism and becomes paramagnetic. Below the Curie temperature, it returns to be ferromagnetic. Typical ferromagnetic matters are iron, cobalt, nickel and some rare earth elements, and their compounds. The explanation of ferromagnetism requires a high level of quantum mechanics and statistical mechanics. We will not discuss its details in general chemistry.